There can never be sufficient evidence exposed at the Earth's surface for the certain and mathematically accurate determination of what exists below. With those words, Henry Gould Busk in 1929 opened his book called Earth Flexures. That book lay out the protocols for drawing geological cross-sections with precision. And as you can see from the subtitle from this book, the principal driver for this was the petroleum industry and the need for better cross-sections drawn to depth. And as he puts it, also in the introduction to his book, geological sections no longer rely for their truth or otherwise on freehand drawing, but upon careful drafting, so far as the evidence will allow, with geometrical instruments. So he was all about adding precision to geological interpretation and provides a protocol and workflow for drawing cross-sections using simple geometric rules. He was one of the first people to do this, and these approaches remain important to the present day, although they've been strongly modified. So in this video, I'd like to go through the Busk construction method. We're going to look at how we can apply it to using surface geology and perhaps some subsurface information from a well, and our mission is to draw a bed through folded stratas, which might, for example, be a hydrocarbon reservoir unit. For Henry Busk, folds were continuously curving arcs, and it's that assumption that underpins his construction method. So remember, this technique was developed in the 1920s, and it was all about great draftsmanship. We'll use some basic drafting equipment. We're going to use a protractor and a pair of compasses and pencils and a ruler to construct our cross section using the Busk method. So let's look at the information we're going to use. We've got a topographic landscape through here, and these symbols represent the orientation of bedding made at various locations along that land surface. In addition, we've got a well that tells us one place in the subsurface where we have bedding, and we're going to assume this is on the formation top that we're going to try and map out. So we're going to construct perpendiculars from that bedding reading, and I'm just going to extend the length of that symbol so we can then now measure from this a perpendicular using our protractor there, and so this is a perpendicular direction from that bedding reading. And now we're going to do the same, and we're going to move this way across our section and do the same for this here. So I'm just going to extend that symbol again just so I can make a reasonable measure from it. There. Put my protractor on this, and we're going to project this perpendicular from the bedding into the subsurface, and we want to see where these 2 points or these 2 trajectories meet. Let's just project those out. So I'm just using the ruler just to extend those off down into this direction here and this direction here, and they meet at that point. Now, if the layer we're constructing is folded as a simple arc, we can extrapolate it as an arc segment about a centre here, like this. So it's time to get our compasses out and construct the arc. So we'll put our compass point into the middle of this, we'll spin that out to collect that point there, and simply construct the arc between these 2 segments. And that's a prediction of the trajectory of this horizon between this point here and this point here as part of an arc along a fold. Now we'll move along to the next arc segment that will exist in here. So we move to our next bedding reading, and again I'll simply extend it so we can make our accurate measurement of a perpendicular to it, like that, with my protractor on, line it all up there, and I'll continue that trend with the ruler like this, And this time our point of rotation will be about this point here. So we'll get our compasses and continue to build out our horizon from the part that we've constructed already. So I'll just pop that point on there. Oops, let's put that like that. I just need to adjust my compass so that the pencil's the right length, like this, and then spin it around like that, and there is the next part of the fold. So let's continue. Next bedding reading is here. Again, you get the idea. We'll extend it so that we can use our protractor more accurately. Like this. Put my protractor on, like that. Measure perpendicular to it, which puts us down here. And our arc, we need to extend back this way, because remember we're looking for the intersection of this trajectory with that one. So I need to extrapolate this one into what is the sky. Whoops, put that a bit tighter. There we go. So there is our rotation point for our next arc, and I'll clearly need to extend that a bit further too. Into the subsurface. To extend the pencil out a bit this time again. Put it on there as our rotation point. Find where our bed is that we're trying to continue to construct, and it's going to sweep around to that pencil line there. So here's our fold, and we've constructed an antiform as our layers come out from our well onto here, around the hinge, which is in the middle of here somewhere, and then around into another sweep. And we can keep going with the same process. So in this case in here, we're more or less on the same point of rotation as we had for the last one. So I'll just extend again our perpendicular into the subsurface, like that. We'll get our arc going. It's the same point. That point should more or less line up, as indeed it does, because it's the same radius. And around we go to here. And then finally, we can put the last one on. Just extend it. There we go. Measure out. Perpendicular. Like that. Extend. Extend that a bit more so they cross in here. So there's our next rotation point. Much shorter this time, so I'll just adjust the compass again to here. And there we go, that's the last piece of our fold. And that's the end of our data. So that's as far as we can construct our layer towards the right hand side of our profile. But what about this side? Well, we just keep going with the same method. But the interesting time this time is that these the bedding in here is parallel to the bedding in here. So these two trajectories will be parallel, and we can demonstrate that if I just construct the normal to that, like this, construct that down, and these two lines don't meet, and that's because these two bedding orientations are parallel to one another. So therefore, in this situation in here, the rotation point is essentially at infinity, making this a straight line segment. So I'll just project that across here as a straight line to that point there. Okay, now let's continue. I'll just straighten this up along to the next bedding reading. So again, put our bedding in here, just to emphasize it so that we can get our protractor on it properly, like that. Project this like that. We can see that this time this line is going to converge with this one in the air. Oops, didn't extend it enough either, so I'll just do it freehand. It's there, and we can now construct our arc. For that, put our point on there. For the compasses, put it there. Whoops, rotate around. I haven't brought that line far enough down, so let's do that. Like this. So there it is. So that's our bed continuing to here. Looks like we're coming down into the bottom of a sin form. Let's put the next line in. Just here. Again, extend it so that we can get our compasses on. And we see that our crossover point this time between this perpendicular and this one is just here. Again, I've not extended that line far enough, so I'll do it now. To here to give a chance for that arc to meet it. Get our compasses on, that rotation point. Pick up the bed trace as it enters our arc segment and swing it around to there. And then we've just got a few more to do. Let's just extend this one. Clearly it's going to match over here somewhere, isn't it? So let's just pop that on. So it'll converge. Oh look, it's actually converging on that bedding reading, but whoops, let's get it tight. Yep, right on that bedding reading, which is coincidental. And let's just extrapolate that over this way so that we can get our arc coming up to it. Pop our compass point on here, back to there, and rotate it around to here. Almost there. Just extend this out to here. Draw the perpendicular on. It's going to take us down into the subsurface to find the match point there. Project that one across so that they meet. So there is our rotation point. Interesting now, isn't it, that we just need to extend that one up into the sky, because what's interesting is our bed that we're tracing out has come to outcrop and is now up in the air. There we go, get that rotation on there, arc it round. And then the final one, just on the edge here, just extend it, almost running out of paper to work. Pop that down, do a bit of extension just to get this in. That's going to come down to there. Just extend that one with the side of the protractor while I'm at it. To there, so there's our corner. Last point, there's our centre, just there. There's the bed trace coming in, and I'll just swing it around. Oops, to here, not quite far enough. Just extend that out so we know how far we're going to extend it to. It's to there. So we've managed to trace out our bed from our well penetration. We traced it over an antiform and into a synform going to the right, and then coming to the left, a straight line segment of constant dip rather than arc, and then around this synform into an antiform in here, which is actually an outcrop. So let's imagine that what we've done so far is to construct the top of a geological formation. Let's now construct the base of that formation, assuming the formation's thickness is 200 meters. So if we look at this, let's imagine this scale bar is 1 kilometer. So 200 meters is going to be 1/5 of that, and as it happens, that's 5 centimeters. So at the scale of the diagram, 200 meters is represented by 1 centimeter. And that's the true stratigraphic thickness, and we measure that perpendicular to bedding. So what we can do on here is simply take our 1 centimetre and measure from our well, and that would be the base of our formation. So now we just need to construct this around the same arcs, and they're going to be concentric upon the shape we've already drawn. Okay, so out come the compasses again, and we go back and join back to these centres of rotation, and this time we can pick the base of our formation here and gradually just step our way around the diagram. So there's that rotation. The next rotation point is here for this bit of arc, so we'll adjust this right down, almost at the limit of the use of this pair of compasses. Too wobbly. Quite tricky with this bit of kit. There we go to there. Now let's go to the next arc point, which is for here, for a rotation like that. So we'll come back out to here, adjust the pencil again in the compasses so that it works properly. Pop it into here. The good news is we can use this arc center a couple of times because it's the same for this one to here, but it's also the same for this one here, so we can just keep running round. It's a continuous curve. And then finally this piece in here, again it's going to be right at the limits of my set of equipment because the radius is so tiny. So I'll just pop it on here like this to there, and just this little segment like that comes around. Okay, so I didn't plot that very well, it wasn't quite right. It was right at the limit of the pair of compasses. Quick check is that this thickness of 1 centimetre on the diagram, 200 metres in our notional layer, should be preserved right the way around. So I can just get my ruler out here and just measure in here just to check that's the case. Not bad. There's a bit of wobble in this because of this little uncertainty, and interestingly that plotting error has propagated on through the rest of the diagram because we're right at the limit of using the pair of compasses. Right, so anyway, let's keep going this way and see if we can do a better job moving in this direction. Obviously in the 1920s they would have used slightly better pairs of compasses. So that segment there is the straight line. There we go, so that should still be 1 centimetre, as indeed it is. And now we can use our compasses to construct the folds out towards the left. So I'll just find that common point there. Like that. The next one for this arc is from here. Set it up, that's about right, there we go, to there. The next rotation point is right on that blob, that was the one which coincided with the site of the reading. So we'll come back to here, get that set up so we keep following our layer to there. We're going to have another fiddly one down in this position, just from there to there. So fiddly one again, and then finally this one down in there. Get it right across, there we go. There. So here we have our horizon constructed through these folds. Starting off at the well, we've constructed the top horizon around here, constrained by these bedding dips, and then having defined these points of rotation through here, we've been able to add another horizon which defines the base of this formation and follow it around these concentric arcs. And in doing so, we've drawn a cross section that predicts precisely the position of the formation in the subsurface and even in this area here that's been eroded. We saw that there was some error associated with the plotting technique. I was using some really crude compasses that I bought from a supermarket. 1920s drafting equipment would be much better than this, and there's an equipment error that came about when we were generating curves with very tight or short radii in our profile. But apart from that, it does a good job. So the Busk construction is a really powerful technique, and it's quick and simple to do. But it does assume that the layers are folding concentrically, in which case the layer thickness is maintained through the folds. And not all folds do that. So that assumption is a limitation on the application of the construction technique. In the next programme, we'll look at the limitations of the Busk construction and some of the consequences for adopting this construction technique for other parts of the cross-section.